Okay, so today let's get into some real quantum field theory now. And when I say real, I don't mean like real in any um, insinuating sense, I guess. What we're going to talk about today is the Klein Gordon equation, right? We've talked a lot about the Schrodinger equation. We talked a lot about the raising and lowering operators in the Schrodinger equation, and how the Schrodinger equation is sort of a mask for the Helmholtz equation, right? By introducing the a couple of reparameterizations in the Schrodinger equation, we found that we come to the Helmholtz equation, and we come to an equation that has raising and lowering operators in it. I want to shift our focus today on the Klein Gordon equation. So the Klein Gordon equation. Now, I could go over the history of this equation, but I won't, because I'm sure Gordon equation. So I could go over, again, like the history of this equation, but I'm sure you guys are, that's the history is easy to look up, right? We can, Klein and Gordon were two guys that were responsible for coming up with this equation. And this equation largely doesn't work, right? This doesn't work, but this was this was the historical, one of the historical underpinnings to quantum field theory, right? Because the Klein-Gordon equation addresses the question of relativity, right? Quantum mechanics, it was the first attempt, one of the first attempts to merge quantum with special relativity. Special relativity, right? And so we're interested. So this is our sort of our first interesting equation that marries these two things together. And we want to start at 2 points here. We want to start by considering the equation that Einstein came up with. This is sort of our starting point. E squared equals m squared c squared, or c to the fourth, actually. I'm going to get all this right here. So m squared c to the fourth plus momentum squared c squared. Right. So this is for a photon, right? A photon has in the case of a photon, actually, in the case of a photon just has momentum. It doesn't have any mass, right? This is energy that includes photons, and photons, as we know, are relativistic. They travel at the speed of light. So this is relativistic energy, right? And so this is the relativity, right? So what I'll do, actually, I'll do this. This is the relativity. I'll put that under relativity. And then we have our quantum, right? Our quantum is our energy operators, our energy squared equals I h bar d by dt. This is our operators. This is quantum mechanics, and we square that because we're squaring this. And our momentum operator, as we've seen, is this squared. So it's basically the opposite sign squared, right? And actually, the squared goes on the outside of the braces. So it's these guys here into this guy right here. So this is the actual addition of quantum and special relativity put together. So let's see what we get when we do this. So I'm going to put this operator into here. So we're going to have, let's see here. I'm going to have I h bar d by dt squared, and we're going to have this act on some wave function to a particle, because this only works on acting. These are operators. They have to act on something. Right, then we have our m squared c to the fourth, so I'll just leave that as b. M squared c to the fourth, that has to act on a wave function. And then we have our other operator, our p squared operator. So this is our h bar over I squared, and then c squared d psi. Right, so this is literally just putting these guys into this guy, right? This is quantum plus special relativity, right here. That's this step. So let's see where this step gets us. So we can start manipulating this equation a little bit. So if we have, so I could say I h bar d dt, and I'm going to square that, and that's going to be minus, I'm going to bring this guy over, so minus h bar over I, that's a weird h bar, but that's an h bar, squared. Okay, and these guys have to operate on wave functions. And then we have our c squared here operating on a wave function. And then this guy's going to stay on this side of the equation for right now. What I'm doing is I'm deriving the Klein Gordon equation, right? If you already know how to derive it, then you don't necessarily have to watch this video. But at the end, I'm gonna talk about the solution to the Klein Gordon equation, because again, the Klein Gordon equation is a differential equation, so we need to have solutions to differential equations to model our systems, right? So I'm literally just manipulating this around. I can get rid of the i's, and so by doing that, I'm going to get negative, because I squared is a -1, so actually that's just going to be negative. And then I'm going to have h bar d by dt, and then that's a squared operator, so the second derivative acting on psi. And then I'm going to have h, that's squared actually, minus, or actually plus, because, let's see, this squared is going to be -1, and then times that minus right there is going to give us a plus. So it's going to be h bar squared, and actually that should not be squared right there. That squared, c squared, like that, and then again m squared, c squared, or c to the fourth actually, c to the fourth times our wave function. If we can continue doing more and more manipulations, right? So I can take an h bar out. I can actually take an h bar squared out. And what we get is d by dt squared, or not the double derivative, acting on psi, but I'm actually going to take psi out also, because I'll show you why. Plus c squared psi equals m squared c squared psi, like that. All right, so literally all I've done is I've taken an h bar out, and I've taken a psi bar, or a psi out to the side to make it look like an operator acting on the wave function. Right, and then I can divide everything out by h bar, and actually I keep on putting a squared here. That should be c to the fourth. So I can divide both sides by h bar, right? If I divide both sides by h bar squared, I'm just going to get that, right? And then I can do, I can divide, I can do 1 over c squared here, d dt. This is double derivative squared psi equals that. Yeah, I'm being lazy. I'll just write it. And so that's going to be m squared, c to the c squared actually now. That's a good thing I actually wrote it out. Was not lazy. It's squared because we're dividing everything out by c squared, right? All right, this is the Klein Gordon equation, right? This is actually, so it wasn't that hard to come to this equation, right? We took some postulates of quantum mechanics. We said that energy, again, is this operator, and the momentum is this operator. When this is our relativistic equation. And from all of this, these are the three, this is basically the three axioms. 1, 2, the three things that we really just need to derive the Klein Gordon equation, which is this. Now, there's a couple things to note about the Klein Gordon equation, right? So this m right here, photons don't have mass. So in the case of a photon, this becomes just a wave equation, right? Because this is going to be 0. So in the case for a photon, this literally just becomes 1 over c squared d over dt squared, like that, plus psi equals 0, right? And so from that we can say, from this, we could say that 1 over c squared times a double derivative with respect to t times psi is equal to the negative of the derivative with respect to space on psi. And this is just the wave equation. So for photons, for a photon, it literally just becomes the wave equation, our Klein Gordon equation. So so this is that becomes 0. This whole side becomes 0, or the 0 vector, to in the case of a photon, because photons don't have mass. Now, let's take a look at this a little bit more, actually, because what if we want to apply this is going to be interesting. This Klein Gordon equation becomes interesting when we begin to look at objects that do have mass. Right, so the Klein Gordon equation, like I said, it can be rewritten. I'll just rewrite it to look like this. So it looks d dt minus squared. This is our operator, and its eigenvalue, the eigenvalue for this operator, is m squared c squared over h bar squared psi. This is our eigenvalue, right? This is our operator. And this is our eigenvalue. Eigenvalue. And so yeah, so we have an operator and we have its associated eigenvalues, right? Like we had with our Schrodinger equation, we had our Hamiltonian. We had our Hamiltonian and acting on psi, and that was equal its operators, the operator acting on psi. In the Schrodinger case, so this is interesting to note, in the Schrodinger equation, right here, its eigenvalues are energy. So in Schrödinger case, the eigenvalues are energy. So eigenvalues are energy, right? In the Klein Gordon case, right? In the Klein Gordon case, we can clearly see that the eigenvalue, okay, well, these guys are constants, right? C and H are constants, or C and H bar are constants. The only thing that's really not a constant is the mass, right? So the eigenvalues for the Schrödinger for the Klein Gordon equation is this proxy for mass almost. It's m squared, right? And this is so this is an interesting thing to note, right? Sort of right off the bat when we derive the Klein Gordon equation, it's the eigenvalues that we get for the Klein Gordon operator. This is the Klein Gordon operator. Our mass, or in terms of mass, we can is the mass of the particle. So we can go back to our picture of operators reaching into our bag of Hilbert space, if you will. I've talked about this, right? For every point in space and time, we have a Hilbert space, right? We have this Hilbert space, infinite dimensional Hilbert space, and we have an operator. In the case of a photon, we have an operator that reaches in to our Hilbert space, and it extracts vectors, eigenvectors, in that space, eigenvectors. This is a call for photons, or not just for photons. No, because we have mass. Photons don't have mass. The eigenvectors are again psi. But it also has eigenvalues. And those eigenvalues are associated with the mass mc squared over h bar squared. Right? And so this is sort of the first interesting thing to note about this. What about the solutions? So we've talked about deriving the Klein Gordon equation. That wasn't too bad, right? We literally just took these three postulates, if you will. They're not really postulates, but these three guys right here, and we derived the Klein Gordon equation with ease, somewhat. And then we talked about, okay, the Klein Gordon operator. Its eigenvalues are closely associated with mass, or the mass of the particle. What about the solutions? What are the solutions to this equation? Well, we can take a guess. We said that this looks an awful lot like the wave equation, right? Especially when in the case where we're just talking about photons or things with no mass. So let's postulate, let's guess that our solution to the Klein Gordon equation is a wave, right? And we'll say it's e to the negative I h bar et minus px. So this is a wave, right? Because remember, whenever we have I in the exponent of e, that's a wave. That's an oscillatory function. We can go back all the way to calculus to show why. When we're doing Taylor series and all that kind of stuff, we can prove that this is a wave. But we can put this into our operators. dt squared, or this second derivative of psi, if psi is this, well, that's going to be let's see, that's going to be E. We're going to do this twice. EI over H bar times EI over H bar times our wave function again, e to the negative I H bar E t minus px. Right, we bring this down twice because we're taking the double derivative. And then that ends up being negative E squared over H bar squared times our wave function back again. Right, and same thing with our nabla operator. What we're going to find acting on psi is that this is equal to just the inverse, or not the inverse, but the positive. It's going to be positive p squared, because we're doing this process again, but with this negative right here, it's just going to flip our sign. I'll just put psi again. E psi. All right, and then so if we plug our solution back, we have 1 over c squared times E squared over H bar squared. That's this part right here, minus, or actually, let's see, so this guy right here, that's this right here, that's going to be p squared over H bar squared, and I think that should be a plus because that should be a plus, right? I think because there's a plus right there, yeah, when we did that derivation. So we have that equal to m squared c squared over H bar squared psi. And we can see that we actually get our Klein Gordon equation back. So we see that this wave is a solution to our Klein Gordon equation. But more generally, what's interesting more generally is that this wave, another solution, our total solution, our most general solution is this. Et minus px plus e to the negative I over H bar, or not negative actually. This is, because this is, we can find that this is actually going to work as well. Et minus px. So this here is our most general solution. This is so our Klein Gordon solution. So, but again, this actually isn't our most general Klein Gordon solution, as we'll see later. We can add, there's a few things more we can add to this generalized solution to make it even more general, right? But so let's just recap really quick. So we went through the derivation. We went through the derivation from these three starting points. And then we took a look at what the Klein Gordon looks like in the case for a photon. And that's really just the wave equation. And then I rewrote it, and we made note that the Klein Gordon operator is associated with just multiplying our eigenvalue or our eigenvectors by our eigenvalue, which is associated with the mass of the object, right? Again, this isn't the case when we're talking about particles that have mass. And we compared that to the Schrodinger case, where the eigenvalues are associated with the energy and not the mass. And then we took a look at the solutions to this differential equation. Right? This right here is a differential equation, the Klein Gordon differential equation. And we found that a general solution to the Klein Gordon equation is a series of complex waves, right? So this is one complex wave, in which case we got positive energies, right? Because when we put this back into the Klein Gordon equation, right, this negative, I missed a negative somewhere. This here, I believe. Let me see here. Okay, I think it's going to be a little bit too time consuming to track down that negative, but the point is that the solution, the Klein Gordon equation, is a wave equation, right? And the wave equation has wave solutions, which look like this. And so let's take a look now at these solutions a little bit more, and how we might be able to generalize them a little bit more as well. So let's see here. So I actually found out where that negative went. It's right here. Right, so this is going to be negative, and which means, yeah, so I fixed that. So all of this still holds, right? So this is the Klein Gordon solution that we have so far. So these are waves, and these are waves that are associated with different energy types, right? We have a positive energy type, and for this wave, right, this is a positive energy. Positive energy. Actually, no, energy. Different types of moving waves, right? Because in this case, we have positive momentum, negative times negative. Right? So this is positive momentum. I'll just put a P there. And this one here is negative momentum. So we have, these are just opposite directions, right? So if we were to consider this to be the positive direction, the particle, in this case, is moving in that direction, right? If, again, we're taking this to be the positive direction, then the particle is moving in this direction for the negative momentum solution. Right, so out of all of this comes this type of solution. And we can expand on this a little bit more, actually, because we could put arbitrary constants out in front of here. So we could say, I'll erase this, we could put arbitrary constants right here. I'll put a constant right here. That doesn't change the form of the solution, right? So this is actually a solution as well, right? And what's interesting is that when we put constants out here, the constants, if we put a little subscript now, I'm going to put a subscript on these guys. So subscript n, right? Because we want to keep in mind, okay, so again, these are just constants. Our solution is a wave, right? The solution to the Klein Gordon equation is a wave. And we can scale that wave up and down, and it's still a solution, right? So that means our probability function, or our state function right here, takes the form of a wave. Now that wave can have different frequencies, right? And that's what that's it can have different frequencies. It can have different amplitudes. So like this is a solution to the Klein Gordon equation, for example. This could be a solution to the Klein Gordon equation, right? We have a higher frequency wave. This could be a solution. Right, these are all solutions, right? These are all solutions, KG solutions. These are all solutions to the Klein Gordon equation. And what we're gonna see here is that if we put constants out here, we would and we associate one constant, these constants with a particular frequency. So a wave with a particular frequency n, right? If we remember, energy is related to the frequency of the wave, right? So we're going to put an n subscripts on these e's, right? And then we can actually sum over all of these. We can actually sum over all of this to get an ultimate, so to get the most general solution. Let's take a look at the most general solution. So our KG solution, our Klein Gordon solution, is equal to the sum over all frequencies starting at the first frequency and going to infinity of a sub n e to the negative I over h bar energy at a particular frequency times t minus px, right? And then plus b sub n e to the I h bar e sub n t minus px. Right, so we're summing over all of the frequencies, right? These are all frequencies. So what would this look like? Because we can start to begin to see how Fourier analysis might actually be of interest to us in quantum field theory, right? Because this is sort of screaming Fourier analysis, right? Because our Fourier analysis says that we can create a wave, a complex wave that, say, looks like this, and then it repeats like that. There's a complex wave, and this is a sum. This is a sum of more simple waves. So say it's a sum of this wave plus this wave. These all have different amplitudes on them. Plus this wave, plus maybe some shifted waves as well, right? And we can do this for n. We can do this out to the nth wave, nth simple wave, right? So this is going to be our psi. This is our solution, and it's a sum of all these other solutions: psi sub 1, psi sub 2, psi sub 3. This would be psi sub 4, and psi sub n, right? These are all solutions to this right here is a solution to our Klein Gordon equation, and it can be decomposed into other more simple solutions. Right, and what we're going to find, right, if we, I think I might actually stop close to here because this is sort of the extent of our analysis for the Klein Gordon equation, right? We could go deeper, and I think I will go deeper into this, but I don't want to. I think I have like 2-hour-long videos. I don't want these to go on for too long, but that's the point. So what do we have so far? Just as a recap, we have that we started off with this equation, right? These are really the only things we started off with, right? We started with these operators that we sort of developed over the course of these lecture series on the energy and the momentum, and we also started with this special relativistic principle, not just for photons, right? Because for photons don't have mass, so this actually works for photons, but this also actually works for objects that have zero momentum, right? Objects that are moving. For objects that aren't moving, this becomes rest energy, right? For objects that aren't moving, we get E equals mc squared, right? This is that famous Einstein equation, right? For objects that are moving, we have a non-rest mass, or a moving mass, right? So we start off with these guys and we deduce the Klein Gordon equation, right? And then we said, okay, here's the Klein Gordon operator, and associated with the Klein Gordon operator is this eigenvalue, right? So this is the operator formalism. This is the operator formalism of the Klein Gordon equation. And we said that the eigenvalue contains this mass element in it, right? And then we came up with solutions. So what's psi? This guy right here. Psi is a wave. So, and we said psi is a wave, but it can be any wave, right? This is the wave equation, right? For photons, but also for objects that aren't photons. Because remember, this is just a constant. And so what we end up getting is this as a solution. And then we said, well, hey, so these are waves, right? These are waves. There's nothing really stopping us from saying that any wave is a solution to the Klein Gordon equation. And that would be this right here. This could be this right here is a complex wave, and it's a solution, right? And this is a function, right? This wave is a function of space and time. And so our solution, again, so this is our solution as a wave, right? Nowhere have we started to talk about spin, right? And this is probably what I'm going to get into in my next video, is that nowhere have we invoked spin. So spin, what is spin? I'm going to hope that maybe you guys kind of know what it is. I might go into it in depth a little bit. But we want to start talking about spin, because this spin is going to ultimately lead us to the Dirac equation. The Dirac equation. And so we'll have at our arsenal now. We'll have in our toolbox the Schrodinger equation, the Klein Gordon equation, and then we have to talk about spin, and we're going to develop the Dirac equation. And the Dirac equation is really where QED and QCD starts, because that's where interesting things happen. When we have a spin of, say, 1/2, this is the Dirac equation. When we have a spin of 1, we're going to get the Proca, P-R-O-C-A, Proca equation. And we're going to see how, right? How does a spin 1/2 obey, how and why does it obey the Dirac equation? And how and why do spin 1 particles obey the Proca equation, right? And then from there we're going to start talking about Lagrangians and what states look like, what solution states look like for all of these guys. This is to get you excited. So we're gonna. I'm thinking I might. Before I touch on the Dirac equation, I'm thinking I will go over spin first, because nothing's better than a little bit of a refresher on some old topics. So with that being said, I hope you guys enjoy this one, and I'll see you in the next one.